paper. The challenge here is that you have to look at your flat two-dimensional drawing and acknowledge the fact that there are three dimensions to it. We learned how to draw the wedges, the dashes, and all that in chapter 2 or chapter 4, I forgot, where we talked about the drawing to give a three-dimensional aspect to a bond. And we said, okay, well, every sp3 carbon is going to have four bonds, of course. And the way that a tetrahedron works is that every time that you have a tetrahedron, every time, and this happens no matter if the carbon is in a ring, even if the carbon's in a ring, we already know about pairs. Down, up, down, up, down, up, angle, 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 and angle. Even these carbons are sp3 carbons, and they will have, in a plane, the plane of the written paper, the plane of the board, we have the two hydrogens that are symbolized with a covalent bond that's a single straight line. These will be on the plane. So if I were to put this up here, it's as if I were able to show you that this hydrogen is this one, that this hydrogen is this one here, this one, this red one, is the one coming at me with a solid wedge, and the dashes is this one down here in the next room.
Get me a better camera, Ashley.
So every tetrahedron is like that. Is that okay?
Yes.
All right. So let's practice on the model finding planes of symmetry, so that we can understand what a plane of symmetry is, and then we can interpret the drawing and on the flat paper where these planes of symmetry are going to be when things get complicated. According to our definition of a chiral carbon, a carbon that possesses the property of handedness or chirality, is this carbon a chiral carbon?
No.
Why not? Because two of the things on it are the same. So a chiral carbon is going to be a carbon that has four different things around the center. This one is not that. Because it's not chiral and it has two things around it that are the same, it has a plane of symmetry. Let me show you the plane of symmetry. It's here. That's the plane of symmetry. It's right here. Let me do that again. Let me show you the plane of symmetry. Do you see these two things that are the same? You see these two things that are the same? You pick the two things that are the same, and you go straight down the other two so that they reflect on each other. It is a plane of symmetry. In other words, a plane is defined as what? 3 points. A plane is, that's not even chemistry. A plane is defined by 3 points. What does 2 points define? A line. I got all Euclidean on you now. But remember, a plane is defined by 3 points. What are the points? 1, 2, and 3. So the plane that bisects the carbon atom, whatever this red thing is and whatever that blue thing is the plane of symmetry. Because when I look through the plane of symmetry to the pieces that are left on the other side, I see the same thing. Let me show you. I see one hydrogen reflected on the other. Exactly the same piece. I see half a carbon reflected on the other half of the carbon because the plane goes right through the middle. Do you agree? I see half a blue thing reflected on the other half of the blue thing. I see half of this red atom reflected on the other half of the red atom. So my plane of symmetry goes straight down the middle. Do you agree?
Yeah.
Okay. This compound has a plane of symmetry. This compound is not chiral. Can we agree?
Yeah.
How about if I make the groups bigger? How about if instead of two hydrogens, how about if I made it more complicated? How about if I made it two methyl groups? Yeah, it doesn't matter. Because the plane of symmetry is still the same, even if I had to acknowledge the fact that I had more stuff. So in order to show you guys in the back, the 3 hydrogens on the methyl group, that'll be these 6. My plane of symmetry, the position of my plane of symmetry doesn't change. Look, my plane of symmetry is still the plane defined by these 3 points straight down the middle, so that a methyl group reflects on the other methyl group. It's the identical thing. Look, this is a methyl group, here's another methyl group. I see a mirror between here, do you agree? Half of this carbon on the other half of this red thing on the other half of that blue thing on the other half. Does it matter that these have free rotation? No, because I can clearly see that at any point in time, that I can say, oh yeah, they're exactly the same item on both sides of this plane of symmetry. Are we good? So when I draw a structure, a 3-dimensional structure, and I say, okay, that's an H, this is an H, this is a Br, and this is a Br, this compound is big league, not chiral, because there's lots of planes of symmetry. Is that right? So tell me, it's as if I told you I had 2 pairs of things that are identical. Can you spot the planes of symmetry? Oh my goodness, let's see if I can spot the planes of symmetry. Here's one. Do you agree? Then here's a plane of symmetry. If I were to slice it straight down the middle, half of the red thing on the other half of the red thing on the other half, this carbon on the other one, and this methyl on that one. We okay? Straight down the middle. This one and this one, half of this one and that one, half of this one and that one, half of this one and that one. Do we agree? Straight down the middle. Where's the other plane of symmetry? Isn't that right? Isn't this a plane of symmetry? Wait, this is a more complicated plane of symmetry. Let me figure it out. Where's my plane of symmetry defined by? 1, 2, and 3 points. Straight down the middle. So what happens here? Well, I see the 2 red things on each other. The half of this carbon on this other half. The half of this carbon on the other half. Watch. You ready? Look. If this is contained in my plane of symmetry, this half of this hydrogen on this one, half of this one on that one. This guy on this one. This guy, half of him on the other half. This guy on that one, half of this on the other one. It's a plane of symmetry, isn't it? So this molecule has how many planes of symmetry? 2. All you need to do is find one. If you find a plane of symmetry, the molecule is not chiral. Let's write that down. While this has 2 planes of symmetry, all I need is one to declare it. The molecule or structure of any object, not chiral. The word is achiral. It's achiral. So in the topic of chirality, remember, symmetry is bad. The moment you find symmetry, chirality cannot occur. It will not possess the property of handedness. Yes? Everybody 100% okay? Here's an easy one. Cyclobutane. And to see stereochemistry in a cyclobutane, draw it on a corner. Don't draw it square. It's easier. Here's chlorine, and here's a chlorine. I'll make the other one's H's, make it easy. Does that molecule have a plane of symmetry?
Yeah.
Where is it? Where is it? It's there, isn't it? So that this mirrors this. That carbon mirrors this one. This hydrogen mirrors that one. That chlorine mirrors this one. Is that correct? Yes? How many planes of symmetry do you see there? I see 1. Do you see a plane of symmetry here? No, that's ridiculous. There's no chlorine on the other side for it to reflect. So there's no plane of symmetry there. Is that right? How many planes of symmetry do you see here? How many places of symmetry do you see there?
One.
So I've drawn an obvious one, right? I've drawn an obvious plane of symmetry. I drew it purposely so you would see this one, is that correct? Yeah? Okay. There's another plane. Can you tell which one it is? There's another plane of symmetry. Hmm?
Left to right?
Left or right? What do you mean by left or right?
From,
Like diagonal?
from the center?
No.
Wait, I don't, hold on, I can't tell what you're saying. Excuse me, will I brutalize this fourth thing to a 90 degree? They break every time. They really dislike this. Ring strain. 90 degrees. So tell me, yes, it's not going to cooperate. Because I'm not using the correct one. It really doesn't want to cooperate. So tell me. Let me get the other one up. I made them both up, right?
Do you know where the other one is? Like that, right? Like that?
I don't know.